Hey everybody, welcome back. We've been talking a little bit about hypothesis testing in kind of general terms about the logic of hypothesis testing. And now it's time for us to actually do the thing, right? So we're going to practice with some very simple hypothesis testing. We're going to have a claim about what we think the population average might be, and then we'll see whether our sample evidence is consistent or not with that claim or that hypothesis. We're going to follow the usual stages of a hypothesis test. And these are the same stages that we talked about in this video, which I should link somewhere up there, about the logic of hypothesis testing. So if you want the detailed rundown, click on that link. But in short, here are the stages. Before you even collect any sample data, you should know, what does your hypothesis that you're testing, what does it say exactly? We should write it down explicitly as a mathematical formula, and it's usually of the type that the population average is a certain value. Now we have to contrast that with something, and that would be that the population mean is not that value. And it's traditional that that claimed value about what the population mean might be, we're going to call that our null hypothesis. And our the logical complement of that is going to be the alternative hypothesis. So usually, again, the null is that the population average is equal to some particular value. Let's call that mu naught. And the alternative is the logical complement of that, is the opposite, in which case we would say that the true population mean is not equal to that particular number. The second step is decide on how much evidence do you need to have before you make up your mind. So that's not dependent on a sample either. We're just asking, do you need to have very strong evidence against the null before you reject it, or a little bit less, or even far less evidence? So this is up to you. And this is the significance level of the test. Then we translate that into allowable values for whatever sample thing we would get. And again, we would determine these before we actually collect our sample. So we basically say, what are the charges that you're facing when you go to trial? How much evidence do you need before you're convicted, in broad terms, in probability terms? And then a little bit more specifically, what is that cutoff in the amount of evidence between when you stay presumed innocent versus you just cross that evidentiary threshold, and now you'd reject that and you'd be convicted, you're declared guilty. So all that is pre-trial stuff. And then the trial happens. You present evidence. So you would gather a sample and then calculate a summary statistic from that sample, and it's usually the sample mean. Or it might be some normalization of that mean, basically re-expressing that mean as a z-value. Again, there will be a link somewhere up on top there on what z-values are if you've missed that part. Finally, then you want to compare your sample evidence as encapsulated by this test statistic, and to see whether it rejects or is inconsistent with a particular hypothesis, or is consistent with a particular hypothesis, and we would quote unquote accept it. And then just relay your results. Just conclude your study. So those are the broad strokes. All of that is terribly vague. Let's actually do an example right now. So let's say that you run a factory, and you have a machine that dispenses motor oil into a bottle. So you're in charge of Quaker State or Pennzoil or something like that. And you've seen these bottles of motor oil probably. They come in different sizes. Most commonly they're a quart, or about 32 ounces. And that's when your machine is working well, is that the average fill should be 32 ounces. Now it could be 32 ounces and a couple of drops, or 32 ounces minus a couple drops. But it should be, on average, at least 32, because that's what you're claiming on your packaging. You don't want to fill less, because, well, then it's false advertising and you could get sued or something, or you just piss off your customers. And we wouldn't want to overfill, because then you're giving away product for free. So you want 32 ounces on average, and that's your task. Now, how do you know if you're factory, your machines are working properly? Well, every once in a while, you're going to take a sample of 50 bottles, and you're going to calculate the average fill, the average amount of fluid in those 50 bottles. And if you get a sample average that's way different than 32 ounces, something's probably wrong. So if you get a sample average of, let's say, 50 ounces, your machine's broken. You need to shut down the assembly line and fix your machine. Or if it was filling on average 2 ounces. I think it'd be pretty obvious. Those quart bottles of motor oil would be very light, and you can't charge full price for an empty bottle. So your machine is broken. You need to fix it. So shut down that machine if you're pouring more or less than the 32 ounces. Now we're going to test now this is up to us, at the 5% significance level. So before we've actually ever collected our sample, we decide we want a 5% significance level, or put another way, 95% confidence that our factory is working properly. So, so how do we run this test? Well, our first step is be explicit about the hypothesis. What is our hypothesized mean? Our hypothesized mean was that we fill to 32 ounces. And the alternative to that is that it is not equal to 32 ounces. So these are our two competing hypotheses, the null and the alternative. We said that we're going to be testing at the 5% significance level. Okay, so here we've got our distribution. And this is all normalized, so it's on a z-scale. It's all centered over 0. And I guess our question is, how can we translate 5% significance level to this idea of critical values? So 5% significance means 95% is accounted for somewhere. I'm not sure exactly where. I'm just drawing some lines here. But between these two numbers, we should have 95%. So actually, let's do like this. So 95% should fall into here. And the remainder is going to be out in the tails. Let's maybe switch colors. So the remaining 5% gets split equally in the left side and the right side. So we split 5% in half, and we get 2.5% here and 2.5% there. All right, so we got 2.5 and 2.5 is 5, plus 95 gives us our 100%. Now our critical values are going to be these two particular numbers. How far away from the mean do we need to be until we're in the small tails of this distribution? Now, if we're testing at the 95% level, you got a large sample size, we can presume that the sampling distribution, the distribution of all the possible x bars, is normal. And we can standardize it. It's still normal. And so our cutoff should be 1.96 and negative 1.96. Now we can switch to Excel right now and verify that. And there'll also be a link up on top on calculating probabilities from a normal. So let's switch over to Excel and verify 1.96 and negative 1.96 right now. Okay, so we want to know the value of z that accounts for a particular probability. Now the value of z that we're going to look for is this guy right here. I want to end up showing you that this particular value of z, this is a normalized thing, so it's z's, some particular value accounts for a certain probability. Now it's going to account for 95, so the part in red, plus this 2.5% here. So what value of z, so what particular value is such that the left tail is equal to 95 plus the 2.5, or 97.5%. And that's what we need Excel to show us. So what is the probability? We're going to give it the probability, and we want it to give us back the z-value. So that's an inverse calculation. So norm, standardized, because we're dealing with z's here, inverse, and then we just need to tell it the probability, which was 0.975. Close those parentheses, hit enter, and we get 1.95996, or 1.96, which is exactly what we expected. We could also verify the other number. We want to verify this particular number here. All right, so what probability of z, what value is such that the left-tailed probability is equal to, well, let's see, left of that is only 2.5%. So we'll give Excel the probability. We want it to tell us the value. So norm.s inverse 0.025. And we get our negative 1.96. So our memory serves us correctly, and these two really are the critical values on a z-scale. We're going to do everything on the z-scale. Well, let's write these down. Negative 1.96 and positive 1.96. All of this has been done without collecting any sample evidence. But now it's time to actually do that and run the test. So we've just established our critical values. They're just a shade less than negative 2 and positive 2. So negative 1.96 is one critical value. And the other critical value is right here at positive 1.96. And basically anything inside here is our acceptance region. Where we would accept the null. And anything in the tails is the rejection region. Okay, so that's what we did in the previous slide. Now what happens? Now we take a sample of 50 bottles, and let's say that the average was 31.5 ounces. Now we know everything is going to be working properly if we are filling up to 32 ounces. So I guess the big question is 31.5 far enough from the average to indicate that something is wrong? Well, I guess part of that really depends on, well, how much variation would you expect if things are going perfectly well? Because even a well-functioning machine that's pouring 32 on average is still only doing that on average. It could be a little above, it could be a little below. So we do need to have some idea of variation, even when things are working well. And here, let's just say for the sake of argument that the population's standard deviation is 1 ounce. Now, if we have all this information, we can actually figure out how far away from 32 is 31.5. So, in other words, what we need to do is standardize 31.5. Okay, so here's the process. You take your sample mean, 31.5. You subtract off the hypothesized mean, the mean that tells you everything is fine. So in other words, 31.5 minus 32.0, which is if everything is working fine. In other words, you're filling half an ounce too little. But what does that mean in terms of standard deviations? Keep in mind that we're dealing with averages now, not with single units like single canisters of oil. So the appropriate standard deviation to talk about is the standard deviation of x bars, which is to say the standard error. And standard errors are equal to sigma divided by the square root of n. So what's our standard error? I don't know. Let's see. Sigma is 1 ounce, and n is 50. So that's 1 ounce divided by the square root of 50 ounces. And so that will give us some number, and we'll plug that into a calculator. But what we're looking for then is this ratio, right? This difference expressed as a ratio, a half an ounce in terms of how many standard errors. And if we plug all of this into a calculator, we get negative 3.54. Now let's just pause for a second, because I would rather you guys understand this than just know what to do with this number. If the machine is working properly, right, so if this thing were actually doing, on average, 32, right, well, that's your distribution of x's. Now from that, you can think about what the distribution of averages would be. You could look at the distribution of x bars. And it would, if everything is working properly, it would still be filling 32 on average. But since you're averaging 50 bottles worth, the spread on x bar is going to be much tighter. The spread on this with the standard deviation of x bar is equal to the standard deviation of this guy divided by the square root of 50. So it's still a standard deviation, but we're expecting a whole bunch of stuff really close to 32. We got 31.5. So really, this is 3.54 standard errors less than we would expect. Less than expected, if the machine was working properly and it was filling at 32. Now 3.54 standard deviations away from the average is a long way away from the average. As a matter of fact, on this graph here, 3.54 doesn't even show up. It's so far to the tails. 3 is here. Negative 3.5 is somewhere out here. Man, that's off into the tails. It is a really low probability event that if the machine were working properly with this standard deviation, that we would take a sample of 50 and get an average that low. So even though in practice it doesn't look like, and it's what, it's a half an ounce too little. Well, statistically speaking, this is light years way too small. Like, it's just massively way too small, and it indicates that your machine is broken down. Right? So just to complete this whole process, we had our test statistic, which was a summary of our sample average. It's just normalized so that it's on a z-scale, but it's a summary of x bar, really, and how far it is away from what you expected. And it's way out in a rejection region, one of our two rejection regions. So what is our conclusion? We would reject the null hypothesis. And what was our null hypothesis? That's why we write this down. The null hypothesis was that the actual machine is filling at 32 ounces. So we reject the null, that mu is equal to 32. And we conclude what? Mu is not equal to 32. Machine is broken. So shut down your machine, recalibrate it, something's wrong. All right, let's do another example. All right, so here's our simple, very similar example. This time, rather than motor oil, we're filling cans of Coca-Cola. For the same reasons, over and underfilling can be a problem. And let's say that we know from experience that the average fill rate is 12 ounces. Everyone knows they're 12-ounce cans. And let's say that the standard deviation is usually 0.4 ounces, plus or minus, right, filling. So that's if everything is working well. Now, we're going to test at the 10% significance level if the machine is filling properly. So we're going to take a sample. Let's say we took a sample of 10 cans. And that it looks like we were underfilling by a little bit. Now, we didn't underfill by too much. It looks like it's, little over a half an ounce of underfilling. But still, this is sample information. This isn't just one can that was underfilled. This was the average of 10 cans. So is our machine underfilling? So let's test the hypothesis that nothing is wrong. So we're going to test the hypothesis that the actual average fill rate is 12 ounces. And we're going to do that at the 10% level. So we're just going to follow the same steps as before. Let's be explicit about our hypothesis. Hypothesis is that we've got 12 ounces of filling. So that's if everything is working fine. Now the alternative is the logical complement of this. So in other words, it's not 12. Right? Not 12. We said our significance level was, what was it? 10%. In other words, 90% confidence kind of thing. And then we need to translate this into critical values. Okay. So we need 10% bounds. Now we can just standardize everything so that we're looking at a standard normal. So at standard normal scale, we need two values. I'm not sure where they are. Let's say here and here. That between them account for 90%. So we fill that in. All right, so this is 90%, which means that 10% is unaccounted for and left over. And we can split up that 10% into the left tail and the right tail. And so we should have 5% here and 5% there. So we need to figure out what value of z is here and here that establishes these probabilities, that corresponds to these probabilities. So let's work on this one first. What value here makes all these probabilities true? In other words, you have some random variable z, and we want to know what the left tail probability is. We have a less than sign. So what value here should we have so that this probability is equal to, well, let's see, we have 90 plus 5. 95%, right? You get that less than sign. So the probability that's less than this particular number is not just the shaded in area, but also this part here. So we want to know this particular value that corresponds to that probability. So let's switch over to Excel and calculate that real quick. Okay, so we have Excel. We do norm.s because we're dealing with a standard normal. We're doing an inverse calculation because we specify the probability. We want it to tell us the value of z. And what we wanted was that left tail probability to be 90 plus 5. So we want 95%. And that gives us another familiar z value of 1.64 for whatever. So 1.64. Let's use that. So this particular value of z is 1.64, which means this guy here is negative 1.64 because this is symmetric around 0. All right, so let's write that down. We got negative 1.64 to positive 1.64. These critical values determine our acceptance and rejection regions. All right. So we have acceptance in here and rejection regions here. And these are our critical values. So the only thing left to do then is to take a sample of Coke cans and see whether that sample evidence lies in the acceptance region or in one of the two rejection regions. So let's review what our sample evidence says. So here's our sample evidence. We took a sample of 10 cans of Coca-Cola, calculated their average, and got 11.38, and our population standard deviation was 0.4. So let's summarize all of this information into a test statistic. Essentially, what we want to know is how far away from what we were expecting were we? We can express that in terms of standard deviations or standard errors. So we took a sample of 11.38 ounces. Now that was different from the 12 ounces that we were expecting. Now let's express this difference in terms of standard errors, because we are dealing with averages. So the standard deviation of averages are called standard errors. Standard errors are equal to sigma, this 0.04, 0.4, divided by the square root of n, square root of that sample size. Okay, and so this whole thing then tells us how far away from 12 were we. So if we key this into a calculator, we get the following number. We get negative 4.90. That's our test statistic. Now we said that our critical values were negative 1.64 to positive 1.64. So that was one critical value, and this was another critical value. Rejection regions here and there. Negative 4.9 is way off into the tails. It's, in fact, it's like somewhere almost here, almost negative 5. We're way off into the rejection region. So what are we rejecting? We reject the null hypothesis. That word. Our null hypothesis was that the actual fill rate was 12 ounces. So what do we conclude? We conclude that the actual fill rate is not 12. There's something wrong with our machine. Shut it down and recalibrate. All right, let's do yet one more final example. This time the critical difference is going to be that we don't know what the population standard deviation is. We don't know sigma. And so we're going to have to use an estimate of that. We'll use the sample standard deviation. We'll use S as a proxy for sigma. But since now we have two sources of uncertainty, we've got random sampling problems, and then we got uncertainty on mu, and then we got uncertainty on sigma. We're going to have to use a t distribution. Other than that, I mean, that's pretty much the only really meaningful difference. And I think that's a minor one as well. But let's do the example. So we're still dealing with Coke cans, but we're going to take, we're taking a sample of 10. And this time, let's say that we filled a little bit more than usual. Just 12.07 rather than 12. Now, is this cause for concern? Do we need to shut the machine down again? All right, so we're going to test the hypothesis that nothing is wrong and that the true average really is 12, despite what we got from a sample. We're going to test at the 1% significance rate. And then the real meaningful change in this problem is that we're not going to use sigma that we know. We're going to use the sample average. But since we're using this estimate of sigma, we need to use the t distribution for our critical values. The process is the same. We need to write down our hypotheses. So our null is that everything is working fine and that we are really filling at 12 ounces. And the alternative is that we're not. So it's the logical complement that our machine is broken. We're testing at the 1% level. And now we need to figure out our critical values. So there's going to be some value of t. I'm not sure exactly what, but it probably is somewhere around here. So we're going to have our upper critical value, some value of t, and our lower critical value. And between them, we're going to account for all but 1%. So in other words, 99% is going to fall below these two critical values. All right, well, if 99% is between these two values, then 1% is left over, which means 1/2 of 1% goes to the left and 1/2 of 1% goes to the right. So right over here, whoa, that was cool. So 1/2 of 1% is that, and 1/2 of 1% there is that. What that means is we're searching for some value of t where we've accounted for 99.5% of the probability. So in other words, we need to find this particular value such that to the left of that value, that less than, we've accounted for 99.5%. Just like we did with when we were using z's, except now this probability is calculated from a t distribution. So let's switch over to Excel and calculate that real quick. So we're doing an inverse calculation, but from a t. So t dot inverse, and we need to give it the probability that we're looking at. That's the 0.995. And now it needs the degrees of freedom. Now, for our t distribution, the degrees of freedom is 1 minus the sample size. So 10 minus 1 is our degrees of freedom. Or we could have just entered 9. We hit enter and we get 3.25 roughly. So that's got to be our critical value, 3.25. And then we know right here that's 3.25. And this guy here is negative 3.25. And positive 3.25. Now the thing that's left to do is actually calculate, like actually pull the sample of 10 cans, construct a test statistic, and then see whether our test statistic is inside here, the allowable range of sample averages, or in the tails, which would indicate that our machine is broken because we're in a rejection region. All right, so let's keep working. Our critical values, we said, were 3.25 and negative 3.25. And now it's up to us to figure out where are those critical values. Where's the test statistic? Is it in the rejection area, out in those tails, or is it in the acceptance area? All right, so let's construct our test statistic. We basically just plug in values just like before. This time we're going to use S rather than sigma, but that's the only difference. So we filled it 12.07 ounces. That's 7 ounces more than what we should have had. And then divide by the standard error, which is 0.8 divided by the square root of 10. So let's key this into a calculator and see what we get. Plugging it into a calculator, we get 0.277 for our test statistic. Now that puts us right here. 0.277. We are squarely in the acceptance region. We're not at all into the tails. So this is completely allowable variation for a sample of 10 Coke cans. Nothing to worry about here. So we conclude that we accept the null hypothesis that the mean fill rate really is 12 ounces. The machine is not broken. Or at least we don't have enough evidence to overturn the claim that the machine is not broken. All right, so that's it. Now go forth and practice some of this stuff, and I'll catch you next time. Thanks.